Julapalooza number 3, last one. Okay, so now you've seen a lot of things. You kind of know what to expect, how this is going to proceed. So let me tell you what our scenario is. In this case, we've got a cart, the same kind of cart we had before, where there's no friction unless it hits a rough patch, except it's attached to a pulley and there's a string and it's attached to a secondary weight. All right. Now the weight of the cart is 500, but the weight on the pulley down here, all right, this guy is only 0.2. All right. So we're going to release it from rest, and we want to know how fast is it going to go once the pulley has dropped 25 centimeters. All right. So there's our delta H. Okay. Now, to no one's surprise, we start off with our usual equation. Delta K, all right, minus delta U G, okay? No spring, no friction. We only need this particular term here, okay? Now we're looking at this thing as a whole system. So you might have been a little bit worried. It's like, oh gosh, do I have to do this with every single piece? Do I have to do it with the cart and then do it with the weight that's hanging? No, we're going to do the whole thing. So really what we have here is we've got the cart, the hanging mass, earth, system. We got 3 objects in our system here. Okay. Now the cart and the little hanging spring, they're connected together. That's kind of tricky to do. All right. So whatever their velocity of one is, that's the velocity of the other as well. All right, so we're going to presume, and it's a pretty good assumption, the string isn't going to stretch. Okay, so we're not holding this thing together with silly putty or anything like that. Now, our K is always 1/2 mv squared is what we go with, but we need the whole thing that's moving. So we write it in here as 1/2 mass of the cart plus the mass of the weight. And then we'll have V final squared minus V initial squared, like this. Okay. Now our other term is always an MGH, but the cart, the little cart, it's not changing height. So it's got a delta H of 0. So we don't have to worry about it. All we need to worry about is our delta H of our hanging mass. Okay, just like that. And we're good to go. Okay, so we're going to start out from rest. Okay, so that term goes to 0, just like that. I'll do a little bit of algebra here, and we're going to get that V final squared. It's going to be minus 2 onto the mass of the weight divided by the mass of the cart plus the mass of the weight. All right. And again, that's a nice way to group things together because then all my kilograms cancel out. All right. And I need my G and my delta H. Just like this. Okay. Let's get some numbers in here. Minus 2. And then we got 0.2 kilograms over 0.5 plus 0.2 and 9.81 meters per second squared times negative 0.25 meters. Okay, check out our units. All right, just like we mentioned before, kilograms are going to go away. All right, this meter combines with this to get me meters squared over seconds squared, which is good because we've got velocity squared there, and so we're going to need that. All right, put it on our calculator, run the numbers, and what we get is 0.0322 meters squared per second squared. Take the square root of the universe, and we get, hang on. I'm looking at the wrong page. I was doing it all right, except I wrote down the wrong numbers. Our VF squared term is 1.401. And again, I kept an extra digit on there until we get to the end. We take the square root. Here we go. Just like that, okay? Boom! All right, there we go. So using the first law of thermodynamics is very powerful, okay? We could have done a variety of things with this, all right, to make it interesting. All right, so think about some of these things. All right, we maybe could have had our pulley here. So maybe we're pulling the cart uphill. Like this, all right? Now, in that case, we would have had some change in height here, all right? But we'd have to call it something different because we would end up with a change in height over here, okay? So I'd have two delta U terms. In that case, I'd have to take that into account, all right? We could have set it up where not only was it going uphill, but maybe there's a little bit of friction on there. Okay, and in that case, then we'd have to calculate a normal force, figure out what it's not going to be mu mg like that. It would be mu times the normal force. We'd have to figure out what the normal force is in that case. So we'd have to do a little bit of Newton's second law to get a handle on that. But you know, that's not hard to do. Okay. We could have put a little spring down here and said, well, what if we collapse the spring? Okay, you get the idea. So there's a variety of crazy things that we could do to make this thing complicated. But no matter what we throw at it, okay, we still get to work with this relationship up here. Okay, and we just got to flesh it out once we set it up. All right, there we go.